Good day, everyone. Thank you for spending time with us on this webinar to discuss ways we are addressing carbon reduction for our customers. My name is Chris Lyons, your host and moderator for today. I've been working in the energy industry for the past 40 years, with more than half of that time at Solar Turbines. But as you can imagine, I've seen several cycles, changes, and impacts to our business over that time. I started my career in 1979 working predominantly in the Gulf of Mexico, where we experienced the second oil crisis due to the decreased production as a result of the Iranian Revolution. If any of you remember, if you go back that far, the long lines you had to wait just to get gas. But at that time, oil prices doubled in less than 12 months to $40 a barrel, 40 years ago. Today, we're below $20 a barrel after a speculative peak of $184 per barrel in June of 2008. So it'll be interesting to see the next wave of changes and how the energy industry will transition going forward. As an essential business and one that has its factory still in operation to serve our customers, we are concerned with this pandemic and the safety of our employees, suppliers, customers, and all our families and friends. We hope you have the ability to work in a safe environment, and we hope soon we'll be back to a normal mode of operation. I'm not sure what that'll be, but hopefully soon. All our offices staff are working from home, and those presenting today are working from home. So please bear with us if we run into any technical difficulties as we move through this process. We feel we put together some excellent segments geared toward our oil and gas customers, addressing the topics of energy efficiency and optimization, carbon capture, storage and utilization, methane emission reduction, and lower carbon fuel options. So that'll take us about 15 minutes for each of those topics, and then we have a question and answer period at the end. But during this time, if you'll notice in the right side of your screen, you should see a chat box where we'd appreciate if you could put in your questions, and we'll try to address them at the end of the presentation segment. We're also going to do a live polling where we'll get some feedback from you, and you'll be able to see others' opinions on the whole issue of carbon reduction. So for some webinar information, we will have a recording of this. The slides will be available as well, so you don't have to take all the notes. As mentioned, we would appreciate you putting in your questions into the question box so that at the end we can try to specifically address them. Any issues that you may have, you can contact Kim Cruz during this. She's online with us as well. So why a webinar on carbon reduction? Over the past year, we've had considerable interest on this topic. Despite the current and hopefully temporary downturn in the use of oil, we still feel it is an area that will have to be addressed to remain a vital industry over the long term. As you can see from this slide in the diagram on the left, our atmospheric concentration of CO2 is at its highest level in recorded history at just around 450 parts per million. With, if you look at the increasing that over the last 20 years, it's been pretty significant. The middle chart shows the continual rise in ambient temperatures, with the average global temperature increasing just a little over 1 degree C or 1.9 Fahrenheit, higher than since the last 19th century, with the warmest 19 of over the last 20 years, 19 of those have been the warmest on recorded history. So on the right, for people like us who live in San Diego in a coastal environment, we're also seeing sea level rises. And over the last 10 years or so, we've seen a just over maybe 80 millimeters, 3.3 inches. But over the last few years, that acceleration has continued to grow. So a lot of statistics that say we have to be concerned about carbon in the atmosphere. If you also look at this slide, you see the projection. If we continue at the pace we're at now, that the CO2 will continue to increase. And if we don't do anything, the global temperatures will continue to rise, where then it could result in some catastrophes, as we're already starting to see, fires and floods and all kinds of things. So the international or the Intercontinental Panel on Climate Change suggests that we keep it to a temperature rise of 1.5 C, no more than 2 degrees C. So you see that in the future, if we continue to move at the pace we are, we're going to have to deploy ways to reduce our carbon footprint. So on that basis, we'd like to get into our topics. But our next topic is carbon capture, utilization, and storage, being presented by Dan Burns. Dan is manager of systems and operability in our engineering group. Dan has over 30 years of gas turbine development and analysis experience, specializing in system, conceptual studies, mature product diagnostics analysis, operability, and management. Dan has played a key role in the development of many of Solar Turbine's latest generation of gas turbine engines. Dan, please take control.
Hey, thanks, Chris. Appreciate the time that I'll be able to spend with our audience here. And thanks for the introduction. Let's see here. So one of the things that you notice in Chris's presentation, he told us about this problem of higher CO2 in the earth. It's a real problem for all of us, but there is also an economic consequence as well. And that is in terms of carbon tax and trade and also credit, but there's an economic incentive that we have across the world. And one of the things that has been happening in the last decade or so is a relatively rapid increase in pricing authority. So 20% of all greenhouse gas emissions are now under pricing authority, and it's increasing. It's going higher and higher. And the other reality is in the Paris Agreement, in part of their analysis is looking at a range of what would be acceptable to help mitigate this rise. And they're kind of suggesting a target between 40 and 80 tons of, or $80 per ton of CO2. And the reality is now in this country, we have a credit right now, but inevitably across the world, we're going to have taxes everywhere. So one of the things, how does this relate to our solar gas turbines? Well, CO2 emissions, we definitely produce them on our engines. This plot below shows carbon emissions versus power for all our product line, from the smallest engine, our Saturn, all the way up to our Titan 250s. So our products produce anywhere from 10,000 to 100,000 tons per year in carbon emissions. At $30 per ton, that would be $300,000 to $3 million per year cost to our customers. And other incentives include like enhanced oil recovery, which produces a $35 per ton credit under the Q45 benefit. So first I'm going to give you a definition just to get an idea of what they're talking about in carbon capture, utilization, and storage. The first attribute is the carbon capture aspect, or the avoidance technologies for hydrocarbon fuel burning systems. This includes pre-combustion, post-combustion, and oxy-combustion. Methods of separating CO2 from exhaust gas include absorption, cryogenic distillation, and membrane separation. Utilization of CO2, it's a commercial viable product. Remember, it's an odorless, colorless gas that's very plant friendly. Too much of it, though, is not good in the atmosphere. But there's other applications. 230 million tons of carbon dioxide is used every year. Main users are the fertilizer industry, oil and gas for EOR. It's a very productive thing to do to get oil out of the ground. Food and beverage, metal fabrication, etc. Potential future utilization is in fuels, chemicals, building materials, and incidentally, this year, the X Prize called Turning CO2 into Products, there's a $20 million winner determined by how much they can convert and the net value of products. So there's it's a serious thing to look at. The last one is carbon storage. Now this to me is the not the ideal situation since you're not leveraging it as a product and getting some money out of it. But this refers to storing CO2 into coal seams, aquifers, depleted oil and gas reservoirs, and other spaces deep under the surface of the earth. So what kind of applications apply to solar turbine engines? Well, first of all, you can have creation of biofuels with the captured CO2 in our exhaust. One example is the phytonics process. And again, taking exhaust gas emissions, then putting them in this process, these reactors in the back end. It's a modified photosynthesis process, and in their particular bend on this, they create butanol. Recently, we submitted a proposal with our San Diego State, a local university here, and T2 Energy. We didn't win this proposal, but in the proposal, we were looking at what we call better than net zero carbon emissions, since we're also taking carbon dioxide out of the air. But in that effect, we could capture it. It comes out the exhaust of the back of the engine, and in the bioreactors can catch the CO2 and convert it to B100 algal biodiesel. The residual product can be used for feedstock and biomethane. Dual fuel gas turbine could run on this stored B100 fuel. So you could run on natural gas part-time and the stored B100. And incidentally, the professor I was working with told me that with the carbon captured, theoretically, if you were to capture all the carbon, produce the biofuel, that would produce about half the needs for the fuel if that was run successfully with the bioreactors. So what I want to talk to you about now is exhaust gas recirculation. This is to improve the economics of carbon capture. Caterpillar and Solar has a partnership with this outside group that we got to know last year, Enhanced Energy Group, and they're carbon capture experts that came to us to talk about this. This really intrigued us. And this is what we call a semi-closed system. It's basically the intent is to increase the CO2 concentration in the exhaust and minimize the amount of exhaust, so it makes it easier and more economical to capture the carbon dioxide. So myself, along with a gentleman within Solar, Priyank, and another gentleman, Paul Dunn from Enhanced Energy Group, we published a paper for this year's ASME where we looked at pretty detailed simulation of the exhaust gas recirculation. And coincidentally, we also submitted for a proposal with the DOE, which we're a finalist for, to study it even more further. And some of the things that we're looking at, this is for a plus 50 megawatt type power plant. So it would take 3 of our Titan 250s, but we'll study flame and stability emissions, the cost associated with it, simulation optimization, and economic analysis. The last thing we're looking at, we are looking at a potential demo product with one of our oil and gas customers, and that's pending currently. So here's a schematic from the Enhanced Energy Group. And when I was first presented it, the first thing I had to do is figure out, all right, where's the gas turbine in here, and where's the ins and outs? So here's the ins and outs of the gas turbine in this relatively complicated schematic. And the other parts is that I had to consider when I modeled this simulation, where all these bits and pieces and claptrap in here, pumps, coolers, mixers, splitters, and so forth. And so now I built a simulation model around all the pieces that I needed to be able to understand the behavior of the gas turbine. So I modeled both a Titan 130 cold and drive and a Titan 250 hot and drive to understand the effects on both of those engines. So as I said, we had to create special elements that represented all those different pieces that you see in there. And this is more simplified schematic, where you see that air and some supplemental oxygen is needed to do this exhaust gas recirculation. It enters the engine, it goes through, we cool the exhaust, we condense a lot of the water out, and then we recirculate most of the air back, or most of the exhaust gas back into the inlet. And then clean exhaust goes out, and we attempt to sequester all the CO2 in the back end of the engine. So all these, as I said, new elements were created, and also very detailed accounting. I have detailed accounting of like over 800 parameters I'm looking at in this analysis, thermal analysis, and the constituent, non-dimensional behavior is all accounted for, and looking at different EGR levels or exhaust gas recirculation levels and how much oxygen I need to supplement. So the considerations in there is to get a high CO2 out the back end and also watch the lower O2, since you deplete the oxygen as the parts of the products of combustion. So we watch both of those things, watch the non-dimensional behavior, especially the compressor, and the overall optimization. So I want to minimize the amount of oxygen I need. I want to maximize the CO2 in the exhaust. Typically, gas turbines have about 3% molar fraction of CO2 that comes out the back. With EGR, we'd like to push it towards 20% or so molar fraction. That really helps the economics. And part load operation can be lower, once you size the equipment for the full load application. And and trade studies, you want to minimize costs while maximizing performance and also the CO2 capture. So here's some of the resultants that I learned from doing this simulation. Power improves the EGR. That's one of the interesting things. Carbon dioxide is the densest molecule that's involved in the process. So using CO2 as a working fluid, that increases the amount of mass flow through the engine. Since it's more dense, and the gas turbine is a volumetric displacement machine. The efficiency is about the same or less, and the hot end drive improves a little bit more than the cold end drive. But you can see on this particular plot, this y-axis represents thermal efficiency, the x-axis represents power. The blue is the hot end drive characteristic. So here's where we start from here. With a normal operation engine, this is 50% exhaust gas, 60, 70, 80, et cetera. And you can see how I'm increasing power substantially as I add more exhaust gas recirculation. And looking at it from a basis of power and thermal efficiency, this is showing from 59 degrees, 120 degrees, so off ambient type of performance. This is the nominal curve here, and then this is the with 75% exhaust gas recirculation. This particular parametric is the same that is shown here. But you can see from 59 degrees, we lose a little efficiency, but we always gain power in every case. This is a similar plot for the cold end drive. So continuing on, as I said, the other thing is to minimize the required O2 levels determined by combustion analysis. So in our combustion analysis, we did detailed accounting to understand how much oxygen we want to do. We want to minimize the amount of added oxygen there. And we found out we can run with depleted oxygen a fair amount. And this red zone is the area that combustion told me that I could run as far as the mole fraction of O2 into the burner. So this basically tells us how we can minimize the amount of supplemental oxygen that we need to put in the inlet. The other interesting thing is, again, as you increase the amount of exhaust gas recirculation, the exhaust flow decreases in proportionality. So, for instance, at 80% exhaust gas recirculation, you only have about 20% of the flow that goes to the inlet to deal with. So that's what helps size your carbon capture equipment much, it helps with the cost of that. So here I'm going to talk a little bit about carbon capture equipment, and this was provided by the Enhanced Energy Group. Traditionally, carbon capture has been with the amine process, and CO2 is absorbed into liquid, creating a salt, then heated to drive off the CO2. This is typically a high capital cost of equipment and a disadvantage with solar engines. It's better with much bigger systems. EEG's efforts has been predominantly in the mole sieve based capture. That is an absorption process. It's smaller and less expensive than the amine process, and it's better with smaller systems. The one thing, and as I was saying, the absorber size cost scales with the inverse square root of the purity based on the constant volume and dwell time. So you can see from this plot on the right here, as you increase the mole percentage in the CO2, you substantially decrease the cost and size of the equipment. So that's the reason why part of the reason why we're doing this exhaust gas recirculation. Again, ideally we'd like to capture is linear as we increase that concentration. So 7x, if you could do that much, that would bring you up to about 21% CO2 rather than the normal 3% molar fraction of CO2 in the exhaust. So again, the one thing I just wanted to really highlight is that Solar Turbines and engineering, we are taking it very seriously as far as considering ideas of how we can capture carbon or any other ways that we can mitigate the higher cost of CO2, both to the environment and to our customers.